And we can fairly well match up our Agung compositions with our andesitic ash. Unfortunately, these two sources that we've got for our rhyolitic tephra have their own limitations as well in regards to being matched with ice core tephra. They're either too small or they're too far away. To sum up the 3 ice cores we explored, we anticipated finding only 1 layer of volcanic ash, but we found 2. We can identify the andesitic ash that we found as being from the 1963 Mount Agung eruption, but we have yet to actually identify the source for the rhyolitic tephra with any confidence. This is a somewhat unfortunate complication for climate modelers, considering that the source location of the sulfate is an important parameter when modeling atmospheric response to volcanic eruptions. In addition to this, it means that ice core volcanism signals, as we know it, are a lot more complex than originally believed, and so much more work is necessary in capturing and analyzing ice core tephra. Thank you for listening, and I'm happy to take questions.
Since you said about Agung, so it's down south on equator, it's on Bali Island in Indonesia. There's any evidence that, or any records in ice cores in Northern Hemisphere, that eruption, that in Greenland or maybe Alaska?
There's been evidence of sulfate in Greenlandic ice cores. It's not necessarily a focus of ours, but I think it would be an interesting thing to look at. I don't know how much farther it goes past sulfate peak in like the Neem ice core in Greenland. And so I can't really fully answer that question, but I think it's an interesting direction to take it.
Okay.
Awesome, thanks.
Next up, we have Jeff Auger, and he is going to talk about the implications for southwest Greenland from a warming Arctic.
Hello everyone, my name is Jeff Auger. I am a first-year PhD student working with Mayewski, and recently, last semester, I finished my master's working with Sean Burkle. And today I'll be talking about some new findings that are linked with my master's that I'll be using moving forward into my PhD. And that is how weather in the middle latitudes will change with a warming Arctic. Today I'll be focusing on southwest Greenland. I'll be using the term Arctic amplification, which is the enhanced rate of warming in the Arctic with respect to the middle latitudes, but as well as the rest of the globe. As we can see here, the Japanese reanalysis release, we can see that the last 10 years of this record is upwards of 4 degrees Celsius warmer in the Arctic with respect to the 45 years prior to that. So we can also see using a Hofmüller plot, which is the zonal average at each latitude through time, that Arctic amplification began around 2000 to 2005. So why is Arctic amplification occurring? So as the temperatures around the globe are increasing, the temperatures within the Arctic will increase, thus removing sea ice, decreasing albedo, and then increasing the absorption of solar radiation, which then enhances the temperatures at the near surface in the Arctic. This is going to relax the north-south of the meridional thermal gradient and the pressure gradient, which will act to slow down the mid-latitude westerly winds, which will then increase meridional transport as the jet stream and atmospheric waves will become wavier. This will transport more heat and moisture to the Arctic, further enhancing the temperatures, the increasing temperature in the Arctic. And it will also increase blocking events. These are high pressure systems that can persist for a couple days to a couple weeks. This will also slow down the high and low pressure systems, which will then increase drought and flood events in the middle latitudes. So we can also detect Arctic amplification in many other ways. Looking at another Huffmuller plot, we can see that the heights at the jet stream level are increasing due to thermal expansion at a faster rate than the middle latitudes, again, which will decrease the pressure gradient from the middle latitudes to the Arctic. And we're also seeing that using the Greenland blocking index, which is built from the heights at the 500 millibar pressure level, about halfway up the troposphere, we can see that the heights are increasing over Greenland. That's becoming more stable. High pressure systems are occurring more frequently, right around the early, from the 1990s to the present. Again, these blocking patterns are going to force low pressure systems northward, bringing more heat and moisture to the Arctic, further enhancing the temperature increase. So the IPCC has shown that there are two different types of possible outlooks that we will expect for the future. On the left here, we can see that the mean will be shifted, or can be shifted, to favor more warmer conditions. Or on the right, we can see that there can be an increase in variability. That is, there's more extreme events, more extreme cold and extreme warm events. In southwest Greenland, we're seeing both. We're seeing that the precipitation has increased since about 1995 by about 9%, and the standard deviation, or the interannual variability, has increased by about 60%. So we looked, during my master's, we looked for some connections with that, and one of the larger connections was the Icelandic low, as seen here. That's the climatological low pressure in the Icelandic region. And as we can see in two different months, February of 1990, the Icelandic low is very prominent in the Icelandic region. So precipitation was fairly zonal, bringing precipitation, or storm tracks were fairly zonal, bringing precipitation to southeast Greenland, Iceland, and Great Britain. But in February of 1983, we can see that the Icelandic low is very weak and south of Greenland, with a very prominent high pressure to the east. This is due to a 2-week persisting high pressure system that ended up blocking most of the storm tracks, as we can see in the precipitation, to move more northward, bringing the heat and moisture to southwest Greenland rather than to northern Europe. So we saw that there's this correlation between the Icelandic low and the precipitation in Greenland, positive correlation to the southeast or southwest, with a negative to the southeast during the winter and spring months, when the Icelandic low is more prominent due to the expansion of the jet stream. So in conclusion, as the Arctic continues to warm at this enhanced rate, we'll see more heat and moisture in the Arctic, which will further increase the temperatures within the Arctic due to these standing Rossby waves, or these increased events of high pressure blocking patterns. The positive feedbacks linked with Arctic amplification can be seen to also be linked with precipitation in southwest Greenland. So it is fairly likely that we'll see, as Arctic amplification continues, that we'll see more precipitation and more variability in southwest Greenland. Moving forward with this knowledge, I will be looking to construct a multi-proxy climate record within the Arctic and the North Atlantic to see how this has changed over the past couple of thousand years into the present. I'll be bringing Maine into this equation. How has Maine changed with Arctic amplification, as well as the Gulf of Maine, the Arctic and North Atlantic Oceans? And what should we expect moving forward with an increased warming in the Arctic and people living around these regions? So with that, well, thank you for listening. I'll take questions. Yes.
What can we expect from this increased precipitation in terms of the mass balance of the Greenland ice sheet?
Right. So from what I could tell, the precipitation was more variable in the winter, so it was more snow than rain. But I did look at throughout the whole year, and February seemed to be the most variable. So I would expect that the mass balance should be increasing, but that's not what we're seeing during the recent decades. We're seeing that the southwest Greenland is actually melting at a faster rate. So it's likely due to the influx of heat rather than precipitation.